Hi everyone. Today we're going to continue our work in parametric equation. So first we're going to start off with a little opener. We have parametric equation right here, given bounds of t, and we want to find dy dx. The question should also say in terms of t. So let's go ahead and do that. So the first thing we need to do is rewrite this as dy dt over dx dt. And so now we're just going to do some derivatives of our given parameters. And so we get negative 2 sine of t over 3t squared minus 1. Doesn't simplify, that's fine, we're okay with that. Part B, same thing, find the second derivative. Well, remember, in the formula for the second derivative, I have to take the derivative of the first derivative with respect to t. And so that is what I'm going to start with here because this is going to get a little messy. We have to find what I call dy prime dt. So take our answer from A, right, take its derivative, and so we have to do our old friend, the quotient rule. Okay, so feel free to pause, take your time, copy that down, all right? And now, back to the second derivative calculation, right? And so, in order to calculate that, we're going to take dy prime dt and divide it by dx dt again. And so we already found dx dt in the previous part. Okay, so that's just 3t squared minus 1 one more time. And this is just copying and pasting my quotient rule. And so this looks really complicated, but dividing by another 3t squared minus 1 is just going to increase the exponent right there. And so my final answer becomes 3t squared minus 1 cubed. Okay, and then the numerator, don't waste your time simplifying. You know how to distribute and combine like terms. Okay, on to the new stuff. Example 1, find the highest point on the curve from the opener. And so the main thing to understand here is that when it says to find the highest point, you are trying to maximize specifically the y of t parameter. Okay, and so now, the x of t equation, you're basically going to ignore that. All right, and so now this goes back to a Calc A question, right? How do we find a max or a min? And so 4 steps in this process. Step 1, what's your domain of t? Well, we're given bounds, negative 2 to 2. And again, this matters because, remember, we have to make sure our critical numbers fall into this range. Okay. Step 2, take a derivative, dy dt. We already found it earlier, negative 2 sine of t. And now, continuing this step, we have to set dy dt equal to 0. And don't forget to check if anything makes it not exist. In this case, sine is going to always exist, but still you should be in the habit of writing this down, even if it's going to be none. So coming back to sine again, where is sine going to be equal to 0, right? That would just be at t equals 0. Pi is bigger than 2, right? Negative pi is less than negative 2, so none of those work. Okay. Confirm your critical number is a max. It's your choice, first derivative test or second derivative test, right? But remember, the goal here is to find the highest point, right? And so I actually don't have to do any derivative test because I know the maximum y value is either going to occur at one of these endpoints or at this critical number. So you could try to determine, is this critical number a max or a min? But you actually don't really need that info. So I just made a table here, t and y of t, plug in my 2 endpoints, right? Cosine of 2, cosine of negative 2, okay? Those are both going to be less than 1 because cosine is only 1 at 0, right? And so I know when I plug in t equals 0 that 2 is indeed the biggest value. And the last thing is to answer the question, highest point. And so I need the x coordinate. So I plug my t value into x of t, and I get that the highest point is the ordered pair 0, 2. Okay. Okay, so let's keep going. Example 2, same idea, right? We have a new parametric equation here. Find the maximum and minimum y values attained by the curve. So first thing I like to do, oops, not duplicate, is delete. There we go. What is my domain for t? Okay. Step 2, again, this is max and min y values, right? And so I need to find dy dt. A little bit of chain rule, nothing too crazy there. We're going to set that equal to 0. We're going to set it equal to does not exist. Cosine conveniently always exists. And so now, where is cosine equal to 0? So what angles are going to be 2t, right, that make cosine equal to 0? And so that would be the pi over 2, 3 pi over 2. And I like to write out a few more, right? This is something you did back in trig, right? Divide everything by 2 here. And so we get a bunch of angles over 4 that all fall within the unit circle range. So these are all critical numbers, right? And we have an endpoint at 0, okay? So again, you could try to go first derivative test, but we really don't care, right? The question is to find the max and min y's. We know they're going to occur at either 0 or one of these 4 points. So let's just plug them all in back into y of t, okay? And so you can plug them all in and simplify. A little unit circle practice for you, okay? And so what are the maximum and minimum y values that we got, right? The max here is 2, the min is -2. So nothing too crazy. Okay, example 3, same idea, max and min x values. And, feel free to pause, try it yourself, and then come back and hear my explanation here. So step 1, again, domain does not change. That's nice. Max and min x values, we need to find dx dt, set it equal to 0, set it equal to does not exist. Again, sine is going to always exist. Setting this equal to 0. So where is sine equal to 0? So what angles are t minus 1 going to be? So 0, pi, 2 pi, all the pi's, etc. And now I have to add 1 to all of those. And so I get 1 pi plus 1. And now if I add 1 to 2 pi, that's bigger than my domain, okay? Right? If I, write negative pi and add 1, that'll be negative still. So that'll be outside of the lower bound. So no negative answers. Okay, so we just get 1 and pi plus 1. So again, and the max and min x's, I only have to consider 0 and then my 2 critical numbers. So let's make a table. Okay, and now it gets a little bit tricky, right? Cosine of -1 radian is definitely going to be somewhere between 1 and -1 added to 2. So it's not bigger than 3. It's not less than 1. And so those are going to be my max and min x values. Okay, one more. Example 3, find all points of inflection. Now remember, a point of inflection you can think of in 2 ways. The way I'm going to think of it for this question is, where does the second derivative have a sign change? You could also think of it as where the first derivative goes increasing to decreasing or decreasing to increasing. Okay, so before I can talk about second derivative, I need to find the first derivative. So I'm going to start off with dy dx, which again is dy dt over dx dt. And go ahead and do those 2 derivatives, just some power rules, okay? And now the way I did it was, I only have 1 term in my denominator, so I'm just going to divide, right, 1 by that, and then this term by that, which is conveniently itself. And so I get dy dx is 3t to the 2/3 minus 1. We want that thing's derivative, right? That's my dy prime dt. So that's 2t to the -1/3. And so the second derivative, right, is going to be dy prime dt over dx dt. And so we just found the dy prime dt. That goes right here. Dx dt we already did earlier, right? Go ahead and multiply by the reciprocal. And this is going to simplify pretty nicely. 6t to the 1/3, or 6 times the cube root of t. And so we have to find where this thing, my second derivative in terms of t, has a sign change, okay? So I need to set this equal to 0. And again, you should be considering where it does not exist. You never know when that will give you a critical number. There's no way to predict when that will give you a critical number. So you should always be considering it. Okay, in this case, it doesn't matter, right? Set 6t to the 1/3 equal to 0. You get t is equal to 0. Now for this, we do need to confirm a sign change. So we do what is called the concavity test. This is where we check intervals in the second derivative, right? And so t equals 0, second derivative does have a sign change. Plug it into x of t, plug it into y of t. We get a point of inflection at the origin. Okay. All right. So we will call it there for today. Okay. So thank you, everyone, and I will see you next time.